So let's do another example just so you can kind of, again, see what's happening here, what goes on. And so we are given a sub n, which is x to the n over n plus 1. That's not factorial, that's just n plus 1, times 2 to the n. So a sub n plus 1, again, just as I suggested before, everywhere that there is an n, you put parentheses and you put n plus 1. And now we'll pop this into the limit as n approaches infinity of x to the n times x and n plus 2, that's what n plus 1 is going to clean up to be, times 2 to the n times 2, multiplied by the reciprocal of a sub n. And when we do that, everything cleans up really nicely for us. For large n, those two linear factors are acting like 1. And, oops, I marked out the wrong thing here. Sorry about that. This is still there. So the 2 to the n cancels with the 2 to the n in the numerator. Going too fast. All right, so now this cleans up to the limit as n approaches infinity of the absolute value of x over 2. Well, that's a constant as far as n is concerned. When I take n to infinity, that's what I'm going to get for an answer. Done. Now, this is going to converge. This is rho. This is going to converge when rho is less than 1. Now, the absolute value of 2 is just 2, so I choose to write it like that, and you'll see in a minute why I do that. So it's the absolute value of x over 2 has to be less than 1, and this leads us, this is where this power series converges, because that's what we're after. We have to remember to bring this to our answer because we're after the values where it converges. We know in the absolute ratio test we converge where rho is less than 1. So now we're just down to algebra. Now I'm going to expand this. I'm going to multiply both sides by 2, both sides of the inequality. And for the absolute value of x to lie in the interval where it's less than 2, if I were to expand it out, then x lies here along the real number line. Remember, absolute value says distance from center. X is not x minus a, would be distance, distance from a. So the center point here is 0. So this is the distance, one direction or the other, from 0. Well, right here is our radius of convergence. Remember, we are going to get one of three things going on. We're going to get 0, x equals 0, so we only converge for the one single value of x. That's the value where we're centered at, the point of tangency. It would make sense that we're at least going to get that. Or some interval, which is what we've got here. This was number 2. Or the entire real number line, which we saw in the last example. So here, we're done. The radius of convergence is 2. So we go along the real number line, a radius or a distance of 2. There's 2, and there's 2. So our radius of convergence, if you want to look at it like that, would be 2 in either direction. Okay, so radius of convergence for series centered at 0. There's a second example. Let's move on and let's talk about series centered at A. We know a power series centered at A is going to look like this, some output of the function at A. I'm calling that A naught, but that's f of A. And then plus f prime of A, which we're calling A sub 1, times x minus A. So you see the pattern there. So we are going to converge in one of three ways here as well. Either at only x equal A, and now I want you to recognize A is the point of tangency. It is the point around which this power series was built, and we're absolutely positively at A going to get where this power series acts just like the function. At the very least we're going to get is x equal A. So that's what that means, the single point x equal A. Or, like on the last example, we could see that we get a distance away from the center, either to the right or to the left. So for radius of convergence, we're still after this value r. We could still get a radius of convergence that looks like r. Or we can still get x values, even though we're not centered at 0 anymore, we're centered at A, we can still have convergence for any x value that we want. And there, the radius of convergence would again look like infinity. So the only difference here, really, is that our point of tangency is now A instead of 0, and that the distance from the center along our interval is a distance from A, not a distance from 0. So again, a lot easier in practice than it is in theory. So let's practice. Determine the radius of convergence for the following Taylor series. Clearly here, we are not centered at 0. We are centered at -1. Here, A, our center point, our point of tangency, is -1. And I can tell that from the general term. But the process is still the same. I'm still running the absolute ratio test. Now, in the absolute ratio test, when I wrote A sub n and I wrote A sub n plus 1 that I was going to put into my limit, I never put the alternating term in there. We had a long discussion when we learned the absolute ratio test that says if you pick up that alternating term and put it in your absolute ratio test, the only thing you can hope to accomplish is that you are going to confuse the fire out of yourself. So don't do it. Leave that alternating term up there. We're putting this in a limit of an absolute value. We don't care if what's inside is positive or negative. That's why we're just going to leave that alternating term up there and leave it alone. So we have x plus 1 to the n times x plus 1. Hopefully you can see that. If I were to multiply those two things together, those things are the same. When you multiply the same bases, you add the exponents. That's how I would wind up with x to the 1 raised to the power of n plus 1. In the bottom, I'm going to get 3 to the n times 3. Now I'm going to multiply by the reciprocal of a sub n. See how the process is the same over and over and over again? Now I'm algebraically going to cancel like terms top and bottom. Rewrite my limit. And remember that as far as n is concerned, this is a constant. This is my result from my limit. This is rho. There is no n in that. Everything that was involved that had an n in it canceled out. It's all acting like 1. 3 to the n over 3 to the n. the quantity x plus 1 to the n over the quantity x plus 1 to the n. So everything that's left is a constant. When I take n to infinity, this is what I get. I am going to converge when rho is less than 1. So, just as I did before, positive 3 is just going to yield me positive 3. I'm only going to keep the absolute value marks around the x plus 1 term. I'm going to multiply both terms by 3. And that cleans it up. And this is my radius of convergence. This says from the center point of x equal negative 1, the max distance along the real number line from negative 1 is a distance of 3. So my radius of convergence is 3. So much easier in practice than it is to try to talk about it theoretically. There it is. There's the radius of convergence. Now, algebraically, if I wanted to talk about, it's not required on this problem, but where we're headed, I want you to see this. If I were to say, okay, so for what x values is that true? From x equal what to x equal what? Then I would expand it using what I know about absolute value. This says that the quantity x plus 1, notice I've had to drop my absolute value marks now. I can't put the absolute value marks there because I've already applied that information when I expanded this inequality. Now all I've got to do is get x in the middle by itself. So what do? I subtract 1. If I subtract 1 from that part of the inequality, I have to subtract 1 from all parts of the inequality. So the actual values of x along the real number line that this thing converges for is actually from negative 4 to positive 2. But the radius of convergence is not asking you for the interval. It's asking you how far from the center point that this series was built around, how far along the real number line to the right or to the left can I go and pick up x values and put them in this power series and be guaranteed that the power series acts just like the function. And for us, the absolute ratio test says you can go 3 units to the right of the center point at x equal negative 1 and 3 units to the left. That is a radius of 3. All right, I have more information in this lesson. We're going to now talk about the other thing that they'll ask us besides radius of convergence. They'll ask us to find the convergence set, also known as the interval of convergence. So look for the next video and we'll get started talking about that.